Hey, welcome back to Advanced Mechanics. Today we're going to be looking at another Lagrangian example. It is the compound Atwood machine. So you have two different pulleys. You've got pulley one, and it does, just what an Atwood machine does, except on this side there's another Atwood machine connected to it, pulley B, and it has two different masses on here as well. We're going to make some assumptions, but before we do that, we're going to define what our minimum potential is going to be. It's going to be over here. This is where the potential energy is going to be 0, so anything below it is going to have negative potential. Then, the next thing we need to do is make some assumptions here. The first assumption is that we are dealing with massless pulleys. So there's no mass here, there's no mass here. We don't have to deal with rotational kinetic energy. Great. The other assumptions we're going to make are that the combined mass of M1 plus, let's do M2 plus M3 is going to be greater than M1. So these two are accelerating downwards, and this thing is going to be accelerating upwards. The other thing is going to be that M3 is going to have more mass than M2. So in this system, it's doing that, but in this system, it's doing that. Okay, so that's what we have so far. Now we're going to have to put down some coordinate systems here. I'm going to define this coordinate right here, going down, as x. So then this side right here is going to be negative x. And if you want, you could put L1 minus x, but we're just going to call it x. Keep our lives a little bit simple. It doesn't matter if you do it or not. So as this thing goes one way, the other thing will go in the opposite direction. So that's the position of this pulley here. But then we have these two positions right here as well. So relative to pulley B, we're going to have this position we'll call y. And so then this position here is going to be negative y. And now we could write down our generalized coordinates. For M1, the generalized coordinate is simply going to be x. Pretty straightforward. For M2, it's going to be the combination of this part, because M2, this is an M2 by the way, M2 is being pulled this way in this direction here, but it's moving in this direction this way right here. So you have this y, but you have this term right here, negative x. So the generalized coordinate for M2 is going to be y minus x. And then finally for mass 3 is being pulled because of this thing going in one direction, so this thing has to go in the opposite direction. Same thing here, this thing is going down as this thing goes up, so you can have it down, down. And so the coordinates for M3 are going to be negative y, negative x. Once we have our generalized coordinates, we can start thinking about our generalized velocities here as well. The generalized velocities are going to be, well, we have to define a coordinate system, which way everything is moving. Let's say down is the positive direction. So M1 is moving upwards, not downwards. And therefore, for M1, it's going to have a velocity x dot. For object M2, let's see what's going on here. It's going to have a velocity going down, because this thing is going down because of this pulley here. But this mass is going upwards. So it's going to have a positive velocity because of this, but a negative velocity because of that. And therefore, our velocity for M2 is going to be negative y dot plus x dot. So the x dot because this thing is moving down, the y negative because it's going up that way. Finally, for object 3, it's being pulled, it's moving down because of the first pulley. So this is going to be a positive x dot. And then because this one is bigger than this one right here, it's also moving down. So the velocity is going to be y dot plus x dot. for object 3. And now that we have our generalized position, we can figure out what the potential energy is. We have our generalized velocities. We can figure out what the kinetic energy is, and therefore we can figure out what the Lagrangian is going to be equal to. The Lagrangian, gotta keep some space here, the Lagrangian L as a function of x, x dot, y, y dot is equal to T minus V. We have to determine what the kinetic energy is and what the potential energy is. So L is going to equal, let's start with the kinetic energies first. It's going to be 1/2 m1, and the first velocity is just x dot squared. The second velocity, or the kinetic energy, is going to be 1/2 m2, and over here our energy is going to be negative k negative y dot plus x dot. So negative y dot plus x dot, don't forget to square that. Finally, we have plus the last one, which is going to be 1/2 m3, parentheses, we look down here, it's the addition of those two velocities. So it'll be y dot plus x dot all squared. And then we have to subtract from it the potential energies, which is going to be given by this value right here. So the first one, and I guess I could put a minus sign first, the minus sign will eventually distribute out, and we'll look at that in just a second. The first one is going to be m1g x. So that's the energy of this, and because it's below the minimum potential, we'll have to put a negative sign there. So that's the first potential energy. And then the next one is going to be minus m2g, and then whatever the height for the position for object 2 was, which was y minus x right here. So we have y minus x. Finally, we subtract from that m3g, and the position for that was negative y, negative x. Negative y minus x. And I believe that's it. So we can close the bracket here. And to make our lives a little bit easier, I'm just going to distribute this negative into here, here, and here. So I'm going to call all of these positive, 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 and I'll get rid of that negative sign. Or I guess I could call it positive, whatever you want. Here is the Lagrangian that we have. Now we have to do the Euler-Lagrange equation for x and x dot, and then we'll do it for y and y dot. Let's start with x and x dot. The first thing we need to do is figure out what the partial of the Lagrangian is with respect to x. And we go into our equation. There's no x here, there's no x here, there's no x here, there's an x here. So it's going to be m1g, great. Over here, it's going to be plus m2g, but this is negative x. So I guess we could write that as minus m2g. And then the last one, you have another minus x here. So it'll be minus, that's an m3, m3g. Because of the derivative of a negative is still a negative. There is our first part of the Euler-Lagrange. The next thing we need to do is take the partial of the Lagrangian with respect to x dot. And that's going to be, over here there's an x dot. So this becomes m1 x dot. The next term here, we have to do, what is this called? The chain rule. So the 2 here goes to the front, and then you take the derivative of this, which is just 1. So you end up with plus m2 x dot. And then finally, did I do that right? No, I didn't. This is why it's useful to know what you're doing here. This is a chain rule, so I have to bring the 2 to the front but leave this term alone. So it's actually going to be m2 parentheses negative y dot plus x dot, and we close the parentheses there, and you multiply it by 1 because there's a positive x dot here. So the derivative of x dot is just 1, and that's fine. Finally, over here, again, it's going to be something similar. It's going to be plus m3 parentheses y dot plus x dot. Good. Once we have this, we can take the time derivative of this. And so that's going to be d dt of the partial Lagrangian with respect to dx dot. And that's going to equal, so this is actually not so bad. You just have to distribute here, here, this one into here and here, and then just take the derivative with respect to time. The first one, the derivative of velocity is acceleration. So you can end up with m1x double dot plus negative m2 y double dot. The negative sign is because there's a negative right there, plus m2 x double dot plus m3 y double dot plus m3 x double dot. So there's that. And now what is something we can do? We can clean up the x's and bring them to one part, and then you can factor out the y's, bring them to one part. This equation right here has to equal this. That's the whole idea of Euler-Lagrange. So I'm going to set this equation equaling to this. And we're going to end up with m1 plus m2 plus m3 x double dot plus m3 minus m2 y double dot, and it's going to equal this value right here, which is m1 minus m2 minus m3 multiplied by g. And this is our first equation. Great. So this is equation 1. We're going to repeat what we just did here, but now we're going to do it with respect to y and y dot. So let's work that out. Okay, the partial of the Lagrangian with respect to y is equal to, okay, let's be careful here when we do this. No y here, no y here, no y here, great. Over here, no y, great, gone. Over here, we have a y term here, so it's going to be m2gy, m2gy, m2g, just m2g. The derivative of this is just that. Ooh. And then over here, it's going to be m3g times negative 1 because there's a negative y right here. So minus m3g. And that is the y term. The next thing we need to do is take dl with respect to y dot. So let's go back to our Lagrangian here, y dots. There's no y dot here, there's a y dot here, there's a y dot here, and that's it. So we just need to do these two. And this is a chain rule. So the 2 comes to the front, the 2 and this thing will cancel each other out. And then you have to take the derivative of the inside, and it's going to be negative 1. That's where you can make a mistake. So make sure you take the derivative of this, and it's going to be multiplied by negative 1. And we end up with m2 parentheses negative y dot plus x dot multiplied by negative 1. So that is this first term right here when we take the derivative. The second term is pretty straightforward. It's just going to be multiplied by 1. And then we can just say that's going to be m3. And over here, it's going to be y dot plus x dot, and that's it. All right, and then we can clean this up a little bit. And actually, do we want to do that? We don't have, yeah, I guess it's a good idea to be consistent here. So we'll end up with m2 parentheses negative x dot plus y dot when you distribute the negative into here and here, plus m3 y dot plus x dot. All right. We have this. Now we need to take the time derivative of this, and we get d dt of the partial Lagrangian with respect to dy dot. And all we have to do is just distribute here, 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 and then take each of the partial derivatives. So the first one's going to become negative m2 x double dot plus m2 y double dot plus m3 y double dot plus m3 x double dot, and that's it. So we have this, and we can set it equal to this term right here, and we will have equation 2. So what I'll do is I'll separate the x and y's out just like I did in this top equation here. If I do that, it looks like it's going to be, we have a x dot and x dot here. It's going to be m3 minus m2. m3 minus m2 x double dot plus y dot is going to be m3 plus m2 y double dot. And all of this is going to equal the top term right here, and that's going to be m2 minus m3 multiplied by g. This is equation 2. Great. Now the next thing to do is set these two equations equal to each other, or do something and eliminate the y's or the x double dots and see what your system of equations are going to be. I'll do that on the next page. Okay, moving on. Here is our two equations that we had before, and we're going to try to get rid of one of these variables. We'll do this by using the determinant method, and that just means, multiplying both sides by one of these things and getting rid of one of them. Which one will we get rid of? Let's get rid of y first, and then in the next case, we'll get rid of x. So I'm going to distribute both sides in a way to get rid of this y value. I'm going to multiply the top by something and the bottom by something to get rid of that y term. And what I'll do is I'll multiply the top by m2 plus m3. And on the bottom, I'm going to multiply it by, I want this thing to be negative here, so I'm going to multiply it by -1 times this top part right here, and that's going to be m3 minus m2. So you have to distribute this term into here, here, and here, this whole thing into here, here, and here, and then add them together. That's kind of the long algebra that we need to do. Well, I guess we might as well do it. So the first term, the top part right here, when I distribute this and this, we will end up with, oh boy, it's going to be m1, m2 plus m2 squared plus 2m2, m3, 2m2, m3 plus m1, m3 plus m3 squared, that's a 3 squared, and all of this is multiplied by x double dot. Then we're going to add to that. We have to distribute this into here. But you know what? I know that this and this is going to cancel out. So I'll just call it M3 minus M2 parentheses M2 plus M3 times Y double dot. Okay, so I'm just multiplying these two together. Don't need to do much. And then finally, we have to set it equal to this term right here. So equals, and then the distribution of this into here will become M1, M2 minus M2 squared minus 2M2 M3 plus M1 M3 minus M3 squared. Boy, I wish I had a calculator. Times G. So this is the entire top equation. Now we got to do the bottom equation, distribute this term into here, here, and here. All right, well, might as well. So the first term, when you take this and multiply it into here, is going to become negative M3 squared plus 2M2 M3 minus M2 squared in the x dot direction. Then we're going to take this and multiply it into here. So it's going to be negative M3 minus M2 parentheses M2 plus M3 Y double dot. And then finally over here, we have to distribute this term into there, and we will get parentheses negative 2M2 M3 plus M3 squared plus M2 squared multiplied by G. I think that's correct. And now we just add this, 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 and this together and see if anything will cancel out. Let's see here. So we know that this whole thing is going to cancel out. We can get rid of that. Let's look over here. We have a positive and a negative M3. Those will cancel out. Great. We have a positive M2, negative M2. That will cancel out. Great. And I think that's it for this side. Over on this side, let's see what cancels out. We have a positive, negative, that will cancel out. We have a positive and a negative, that will cancel out. And I think that's it. And then we just combine the terms together. So we get whatever is left over, which is going to be M1, M2 plus 4M2 M3 plus M1 M3. I think that's it. And that's going to be in the x dot direction, and it's going to equal this side, whatever's left over here, and that will be M1 M2 minus 4M2 M3 plus M1 M3 multiplied by G. And the last thing to do is just divide both sides by this term right here. So we end up with M1 M2 plus 4 M2 M3 plus M1 M3. And this side goes away. And here we have it. Well, M1, M2, M3, and G are all constants. That's all you have here. So x dot, double dot, is going to equal some constant. And if the acceleration is some constant, we can use the, high school kinematic equations to solve for the position and the velocity at any moment in time. So that's for x double dot. What about for y double dot? I'm going to rewrite this again on the flip side of this page, and then we'll do that as well. All right, so I'm going to repeat what I just did for the y double dot acceleration instead of the x double dot, and we're going to eliminate these two values right here. This was the two equations that we had before. So what do we need to do? We need to multiply top and bottom by something. We need to multiply the top equation and the bottom equation by some value. In this case, we're trying to eliminate m. So I'm going to take this, bring it to the top. I'm going to take this, the negative of it, bring it to the bottom, and multiply across. And I'll just write that down. It'll be m3 minus m2. And on the bottom, it's going to be -1, parentheses, m1 plus m2 plus m3 on the bottom. And we just have to distribute this into the top, distribute this into the bottom, and clean up just as we did before. So again, let's get to it. The first term, well, this is nice because we're going to get rid of the x term, so I just need to write it down. And it's going to be m, can you see that? Yeah, m1 plus m2 plus m3 multiplied by m3 minus m2 x double dot plus, distribute this into here, we will get parentheses m3 squared minus 2m2 m3 minus or plus m2 squared y double dot finally equals this side right here, distribute this into here, we will get a parentheses m1 m3 minus m3 squared minus m1 m2 plus m2 squared multiplied by g. So that's this being distributed into there. Next, what do we have to do? We're going to take this bottom term and distribute it out. It's going to be negative m1 plus m2 plus m3 multiplied by m3 minus m2 x double dot plus, now here's where we have to distribute this into here. We end up with parentheses negative m1 m2 minus m1 m3 minus m2 squared minus 2 m2 m3 minus m3 squared y double dot, and that's going to equal, we have to distribute this into here, and that'll be negative m1 m2 plus m1 m3 minus m2 squared plus m3 squared multiplied by g. Oh boy. Well, the first things first, when we add these two equations together, all of this and all of that is gone. Great. Then we need to look at this and see what will cancel out. M3 and M3 cancel out, M2 and M2 cancel out here, and then whatever is left over here. These two you can add together. Over on this side, we have the M3 and the M3 that cancel, and the M2 and the M2 that will cancel. What are we left with? We have parentheses negative m1 m2 minus m1 m3 minus 4m2 m3 times y double dot, and that's going to equal this side right here cleaned up, and that'll be 2m1 m3 minus 2m1 m2 multiplied by g. And then we just divide this term to the other side. So negative m1 m2 minus m1 m3 minus 4m2 m3, like that. And this term goes away. And that's what y double dot is equal to. What's nice is, once again, these are all constant values. So the acceleration for this velocity is also going to be a constant, and you can use your simple kinematic equations to solve for that. So this is the compound Atwood machine. A little long, but it works out kind of nicely. And that's it. I will see you in the next lesson. Take care. Adios.